Types of radiation, higher tier, topic test. So we've got some sources of radiation. We've got paper, aluminium, and lead there. So name the radiation emitted by X. So X comes through stopped by lead, so that's going to be gamma. Name the radiation emitted by Y. Well, Y comes through and it goes through lead. So it still must be gamma, okay, even though it takes, so gamma is supposed to be stopped by thick lead, so this just might be thin lead, but the point is it's still gamma, because it can't be beta. Beta would have been stopped here, and it can't be alpha. Alpha would have been stopped here, so these two has got to be gamma. And then Z is going to be alpha because it's stopped by paper there. So 3 marks. State 2 precautions that we can take to make ourselves safe around radioactive materials. Well, we can reduce our exposure, we can wear protective clothing, and we can monitor our exposure as well by using monitoring equipment. Any 2 of those for 2 marks. Okay, isotopes can be used, blah, blah, blah. So let's have a look what the question is. State 1 similarity between the nuclei of 1,2,3 iodine and 1,3,1 iodine. Well, they've both got the same atomic number, but I cannot write that. What I need to refer to is the nucleus. So they've got the same number of protons. They've both got 53 protons for 1 mark. I cannot say the same atomic number, okay? State 1 difference. Again, I can't say they've got the same mass number or different mass numbers. All I need to say is they've got a different number of neutrons. So this one's 131 minus 53 is going to give you neutrons there. 123 minus 53 is going to give you neutrons there. Pointless doing the calculation. It's just worth 1 mark. What is beta radiation? It's a fast-moving electron for 1 mark. Complete the equation below. So this is a nuclear equation. So everything on this side must equal everything on this side. So 131 equals 131 plus 0. Okay, I'm good there on the top line. Move to my bottom line. 53 equals 54 plus minus 1. That needs to be minus 1. So 54 minus 1. Don't forget, plus minus 1 is still minus 1. 54 minus 1 is going to give me 53. Okay, the isotope iodine 123 decays by gamma emission. Explain why it's better to use that than that one as a medical tracer. Well, this one must be beta. If we looked at the question, this is where sometimes we have to refer back to the question. I'm having a look now to see. There it is. It's done by your luck. So that's why it's beta. So gamma is less ionizing, so it's less damaging, and it's more penetrating, so it's easily detected. So it goes, it's not going to get stopped by your skin at all. Okay, so it's more penetrating, less ionizing. Top answer for 2 marks. I like this question because it's a bit of a problem-solving question. We've got window A, B, C, and D, and they all are going to monitor types of radiation, because they either cover with different materials. So this one's 3 millimeters of aluminium, this one's covered with lead, this one's covered with thin card. So you can see where this is going, and this is uncovered. So A really should have all 3 types of radiation coming through it, and which it has. Let's answer this question first. What is the purpose of having an uncovered window in A? Because we need to detect the total radiation level given off, okay? Let's see how much of the total radiation is given off. And you can see it's 9,500 there, okay, with alpha, beta, and gamma. Now that we know that, we can kind of estimate or calculate, I should say, how much is given to each window. So we've got window B. Window B, I didn't want to do that. Let me just have a look at what window B is offering. 3 millimeters of aluminium. So really, that should be blocking gamma. It should be blocking alpha and beta. So it'll only allow gamma through. Well, let me just zoom out so we can see that. So it only allows gamma through there. Then I've got window C, which is covered with thin card. So that's going to allow beta and gamma through. It's just going to stop alpha. And then window D is covered with thin lead. So it's going to block everything apart from gamma. And it's even going to block some gamma. But some gamma is going to go through as well. And there's a reason I'm saying that, because of the next question is asking for us to calculate how many of the counts were produced just from beta radiation. Well, in order to do that, I need to see how much is stopped by this window. Not by this window, because this is going to allow all the gamma through and stop all the beta, where this one's going to stop all the beta and some gamma. So I'm going to use this window, which was window B. So I'm going to take, I'm going to get, first of all, my 6250 from there, which is allowing beta and gamma through. Okay, so that's no alpha, that's just beta and gamma. And then I'm going to take away this, because this is just gamma. So beta and gamma there. In order to just get my beta, I minus the gamma there. So it's 6250 minus 5500. And you give me 750. That is a problem solver. Okay, so that can't really be taught. That's just reading into the question there. That you know you've got beta and gamma there. If I want to find out how much beta I've got, then I just take the gamma away. Oh, lovely. Okay, question 4 then. Again, I always read the question before I go back and have a look. I think it's a good technique to use, and it saves a lot of time. And I find sometimes when I read through it, it kind of confuses me, and then I get caught up on things that I don't really need half the time. Explain, giving a clear reason for your answer, which one of the following statements below contains the most truth. So background radiation is completely harmless. Background radiation can cause harm, but to very few people. Background radiation can kill us. Well, that's not true, and this is not true. So for 1 mark, you're going to guess this. And then you're going to say, because it's low-level radiation from its surroundings, okay? From our surroundings. This one then is numeracy, so it's asking to calculate the mean. So I got 27 plus 20 plus 28 plus 18 plus 15. I got 1, 2, 3, 4, 5 results, so I'm going to divide by 5. It's going to give me 21.6. Can I check my answer? Is it lower than my biggest number? Yes. Is it higher than my smallest number? Yes. So it seems right. For 1 mark then, put a tick in a box next to the statement that best explains why the numbers are different. Well, it's not due to experimental error, and it's not due to taking the readings different times a day. It's due, remember now, radiation is a random process, so it's different numbers of radio particles are being produced each minute. That's what it is, and by taking an average, you can get an estimate then. Just the last note, we got 2 pages to go. So again, this is kind of like the diagram where you've got your source, and then you've got a sheet of paper there, and you've got aluminium plate. So whatever's going to come through, some things get stopped. So again, it's a little bit of numeracy, a little bit of knowing that what each type of radiation is blocked by. So how much of the original count was due to gamma radiation? Well, as we know, if it goes through paper and then it goes through thick aluminium, only gamma's left. So if the count rate's still 120 counts per minute at this point, then that must be due to gamma radiation, because everything else is stopped. So we've got 300 to start with. So that's alpha, beta, and gamma. Calculate the count rate due to alpha radiation. Well, so I've got 300 there. So alpha is going to get stopped at this point. So if I take away 250 from my 300 there, that should give me now just my alpha, which is 50. So now I know I've got 250 going through, which is beta and gamma. By referring to the diagram, explain why the count rate due to beta radiation was 133 counts per minute. Well, kind of like I just said, so if we know that 250 is beta and gamma, and 120 is just gamma, I'm going to take gamma away from the beta and gamma, and that's going to give me 130. It's very similar to when you've got the number of protons, it gives you a number, and then the number of neutrons and protons, which is a mass number. To find the number of neutrons, you take the small one away from the big one. It's that sort of thing. And then, let me just straighten this up a little. We've got this pie chart, and it says what the percent... Oh, I didn't want to do that. It says what is the percentage, or what percentage of radiation is due to buildings of the ground. So it's not calculated that for us, but all this is percentage. So you've got 50% there, plus 10, plus 15, plus 14, plus 1 is going to give us 90. Well, we need 100% in there, So 100 minus the 90 I just calculated is going to give me my remaining 10% there. I've seen students try and get protractors there and try and measure the angles, and it's really not that difficult for 1 mark. You just add them all up and then see what's remaining. One natural source radiation supplying 15% of the total is not named, suggests what it might be. Well, that could be cosmic rays from the sun. That's your background radiation. And if you, yeah, I won't go there because that's year 10. Cosmic microwave background radiation, that's your triple year 10. Give one reason why doubling the number of nuclear power stations would hardly affect the level. Well, it's only 1% if we just look at it. So there it is. Look, it's 1%. So if you were to double that, it just goes to 2%. So for 1 mark, you just say, well, it's not going to have any effect at all because it's only contributing a small part. Then it says we've got 60 counts there per minute. But how much is due to radon gas? Well, radon gas is 50%. So I guess I need 50% of the 60, which is half. So that's 30 counts per minute. And the very last question is asking for a reason why background radiation varies from place to place. And it's because radon gas levels vary from place to place. And that is it for 1 mark. I hope you've got something out of this video.